learning digits problem. And so our training data are the coding of digits, first of all, digits 0 to 9 using this 7-segment display. So we talked about it already several times. I gave you some introductory remarks how to deal with the problem. You received a header file which has the encoding of the different digits. And so the first question was, can the set of even and odd digits be separated linearly? So since this is now input data from 7-dimensional space, it's not possible to just plot the two classes and then see if they are linearly separable or not. What you have in principle to do is you have to program the perceptual learning algorithm and see if you can find a separating hyperplane. Who has done that? I already asked before Christmas. All right. Okay. First of all, because I get this strange window again, do you see the exercise sheet?
Yes.
I also had a look at the chat at the moment. Are there still students waiting? I'm not so sure because I have not activated the waiting room. So everybody should be able to enter the lab without any further. Because we have a separate link today. Yeah. We have separate link today. So they probably have to look it up in the message they received yesterday. Because there's no waiting room activated. So as long as they do have the link, they should be able to enter. All right. If you're in contact with your colleagues, please tell them they should use the link from the message yesterday. Okay, thanks. Great. All right. So there was one student indicating that he has tried to answer the question. So yep. All right. So who has found the separating hyperplane for this task? Please indicate, maybe you can indicate it. Yeah. All right. So who had problems solving this question? Maybe. So I already told you in advance that there is a separating hyperplane between the pattern of odd and even digits. So this was a quite good starting to test your learning algorithm. All right, we go into it later. So let's move on to part B. So in part B, the task was to solve 1022 different classification problems. And these classification problems had to be generated by using all possible partitions of the set of 9 digits. And we talked about it, how to do it technically, because you have to enumerate all these partitions. There are 2 trivial partitions, having all the digits in the one set and the other digits in the other set. So these are the trivial partitions, and of course this is not a classification task. So it's 122 different partitions that had to be tested here, right? Okay, so I gave you some remarks. We talked about it, how to program it. And so who has managed to answer part B? And maybe those of you who have answered this question, how many problems of these 122 you came up with a separating hyperplane? So with how many are linear separable? Some numbers. I mean, yeah. Someone wants to give an answer, or maybe we get a couple of answers. I'm currently watching the chat, so you can type it in the chat. All right. Okay. If you can't remember, that's fine. So what I want to do next is I will show you my code that I used to answer question A and B. So let's see if it works, because all right, here we go. All right, so you should see some tabulator stuff in the editor. So what you received was this header file with the encoding of the digits, and we talked about it already, right? So the first thing you had to do was to implement the perceptron. And so I implemented it basically just using a train method. And the C file for this is a bit complicated, because it's not complicated in a sense, but there are more functions or more functions implemented than just the train method. The train method basically summarizes the training process, the perception learning algorithm. That's what we are using for this exercise. Of course, you have to code how you calculate the output of the neuron, right? So you have to have a function that's calculating the output. And this is basically a function all of you should try to understand. How do you program these simple elements, right? And then we have a train method. And the train method is a bit more complicated. The train method does some initialization, right? So you have to initialize the weights using a random number generator. And then you have to implement the perception learning algorithm, including the update of the weights, right? This is just a straightforward implementation, right? And probably you have done it more or less the same way, but not exactly the same way, right? And the important thing is, while you are learning, you have to test after a couple of iterations. Either if you reach the point where you found the hyperplane, so you have to test if all the digits are classified correctly. If this is not the case, and you have not reached the maximum number of iterations, then you continue learning, right? So this is basically what you have to do for learning. And so, of course, as you can see, these are all functions, so you get the answer from these functions. How you separate all this, right? That's up to you. This is just this is an exercise that you fiddle around, that you basically understand how these learning algorithms work. And you've got a good feeling about that you can implement all this, right? What's on the slides. Okay, I don't want to dive too deep into this code. You will find this code now on the Moodle course. The more interesting thing is, I guess, what are the results, right? And the next thing we want to look at is we want to run this code, and we want to solve questions A and B. All right. So all right. So what I'm going to do now is I will start this simulation or this a program now that first of all solves task A, deciding whether linear or even and odd digits are separable, linear separable. Let's start with it. It takes some time. Okay. So what you should see now. So task A, even and odd digits from 0 to 9 are separable. All right, this is basically the answer I gave you already. And so this is the less interesting part. But let's move on to task 1B. So what we see here in the output is the different partitions, right? So you see set number 1 and set number 2, and the digits that are grouped into set number 1 and set number 2 for this particular classification task. And each line means we are training a perceptron, and we indicate if the algorithm came up with a separating hyperplane or not. For this simple partitions here, right in the beginning, we do see a lot of separable classification tasks, right? There is one here that's not linear separable. this particular one, right? Okay. So, and we move on, we will see from time to time, there are some partitions where we cannot fit a separating hyperplane between the two classes. All right. So, and we go through, and this is our now 122 lines, different classification types. All right. Okay. So that's the end. And what's the output? The output is that in total, we found 160 of these partitions are not linearly separable. That's not so much. I mean, but the problem is not so complicated. We have 10 training examples, and we are in 7-dimensional space, so they are quite sparse there. So there's a good chance to find a separating hyperplane. Are there questions concerning part A and B?
The professor, can we write the code in Python?
Yes. I said, well, I mean, the straightforward thing is to do it in C maybe, but it depends on your programming experience, right? So it's nothing wrong about coding it in a different programming language. I think it's quite important to really code the inner product and be aware of how things are done, right? The programming language doesn't matter.
Okay, so in the exams, I can use any programming language.
Yeah, you can use any programming language. I mean, for example, if you use MATLAB or some numerical packages, right? Usually they give you the function for calculating, doing this matrix manipulations. And then this is, I mean, of course, this is also fine, but I think it's quite important to use a general programming language and to really find out how you program these learning algorithms.
Okay.
Yeah, that's basically the goal of this exercise. You get a feeling about it, and you get a good feeling, and you programmed at least one machine learning algorithm, a quite simple one, right? Which usually works out.
Yeah, thank you.
Okay. So, okay, this was part 1 and part B. I mean, you should, the result I'm giving here, this 160, I mean, you should end up, did one find a completely different number of non-separable partitions? You should end up roughly in that range of non-separable partitions. Why do I say you should end up? What's the difficulty with it? Any idea? Because I said roughly 160. What could happen accidentally? So when we looked at the code, there was this parameter maximum number of iterations, learning steps that you take. Because you cannot decide in advance if you're going to find a hyperplane. So at some point you have to decide, okay, I'm not going to find a hyperplane anymore. It depends a bit on the number of iterations, right? That you use. Maybe there is a case where you just stopped 1 or 2 iterations before you find the hyperplane, right? So you're wrong in your guess. But this shouldn't happen in all of the cases, right? So therefore, I recommend to check if your results roughly in that order, in that range of order, then you can assume that your learning algorithm basically has been implemented more or less correct. Okay. All right, so this was part 1, the part B of this exercise. Let's move on to part number C. Let's go back to the exercise sheet. And, okay, part C now asks a different question. So, part C is more or less theoretical. So the question is, for which maximum number of digits Q, all partitions are linearly separable? Up to which number of Q can you guarantee linear separability without testing on the computer? Any ideas? So what we are now asking, we've seen the experiment using 10 digits. So Q is 10, right? But we can use only 1, 2, 3, 4, 5, or 6 of these digits. And we can use this up to 16, right? Because we have the hex code digits also. So this is the numbers of Q we can use, the number of training examples. And we can look at these partitions, right? And now's the question, up to which number of Q we don't have to test if the partitions are linear separable. Is there any idea what the question is about and about the answer? What about if we select 2 digits? Can we generate a partition that's nonlinear separable? There is an assumption involved in that. Of course, the training data, the points X, I mean the input data, this is not entirely true here in the yeah. So if we have 2 training samples, the one belonging to the one class, the other one belonging to the other class, do we need to program, or do we need to test it with the perception learning algorithm, or is there a clear answer to it? Can we separate these 2 digits? I guess we can do. There is one, yeah, we can do. If we have 3 digits, What about 3 digits? Who thinks they are? We don't have to test it. So we have 3 training examples, and our input space is 7-dimensional. So we have 3 points in 7-dimensional space. The question is now, can we fit a hyperplane? Between any partition of these 3 points in 7-dimensional space?
Yes, we can.
Yes, we can. Okay. So there is one thing that's a bit. I mean, we have to make an assumption. Which one? Can you imagine?
Well, I guess that not 2 points are the same.
Yes, they are not collinear, so they are not linear dependent, so they don't lie on a line, right? And then you can imagine that there's one point in between the other ones, right? So we have kind of an XOR problem, right? So this is the weak assumption, but this assumption is guaranteed as soon as we get to a lot of input data. So there's no none of these conditions. Okay. So, but if this is not the case, they are linearly separate. What's about 4 digits? Or let's ask the question the other way around. Up to how many digits you can guarantee linear separability? I mean, this is a question which, in regard to Q and K, K is the dimension of input space. So as long as you have less or equal the number of training data as which is equal to the dimension of input space, all problems that you can generate using these training digits are linear separable, right? So we are in 7-dimensional space. So we up to 7 digits, all partitions. When we include 7 digits, all partitions are linear separable. So we don't have to test it. So it becomes interesting as soon as we include 8, 9, 10, 11, 12, up to 16 digits, right? So we will see non-separable constellations in there. And this is basically the task in part D. So the last part of this exercise now explores how the number of non-separable classification tasks increases when you increase the number of training samples. So A and P was about 10 training samples, Q equals to 10, right? And now we look at the results for including more and more training samples and look how the number of non-separable partitions develops. So I show you a plot. Okay, can you see? All right. So what we have on the x-axis is the number of digits that we are using for the classification task, starting from 2 up to 16, all hexadecimal digits, right? And we already discussed that up to 7, right? There are no non-linear separable partitions for these digits, right? So it starts to become interesting when we move beyond 7. And as you can see on the y-axis, these are numbers which are like in the range of 10,000. So this is 50,000, right? And as you can see, we've seen the simulation. We saw that using 10 digits, we have 160 partitions that are nonlinear separable. For 11, the number goes slightly up, but as you can see, the more digits we include, right, the larger our training sample gets, right? The higher the number of nonlinear separable partitions. Okay? And as you can see, the number rises quite steeply. All right? So for practical purpose, this means, because, I mean, this is kind of a very simple classification task. But as you can see, as soon as I have a reasonable number of training examples, right? The situation of having non-linear separable classification tasks becomes quite likely. So this is basically the last answer, or the last part of this exercise on learning digits. So we learned quite a couple of basic things, right? So we learned this learning algorithm works. We can test it quite extensively using partitions. We've done some sorts on what's the relation between number of training samples and dimension of input space, right? And here we see that as soon as we have much more training examples than the dimension of input space, we probably have a non-linear separable problem at hand, right? The probability increases. Okay. So this is basically the takeaway message from this exercise. There was a second exercise on this, on exercise sheet number 3. Again, we were dealing with nope. Okay, this was exercise number 2. So here we had a classification problem that's given graphically here in this plot. And all of you should be able to explain why this is a nonlinear separable problem. This is because the separating, the border for separating the stars from the circles is nonlinear, right? So you need more complex decision boundary, all right? It's not just the line. And the question was now, in part B, that you do some trick. You extend the original inputs x1 and x2, which are given here, by a third input, and you do an expansion of the input data by using the square of the x1 coordinate of the points. And then the question was, what about linear separability then? Is there someone who managed to test this constellation? Is this classification problem? I'm using x1 and x2 as it's plotted and x1 squared as a third input to the network. Is this something that helps with linear separation? So the question is, determine the weights of a perceptron that solve the classification task if these exist, if the weights exist. Do they exist? I mean, probably yes, otherwise it wouldn't make sense to ask this question. I show you a simulation now, and I'm going to stop. Okay, so you see the Octave development environment. That's a clone that's basically able to interpret MATLAB code. It's not as complete as MATLAB, but it works for our purpose. So I tried to solve the problem, and what we are doing now, we try to learn or try to find the separating hyperplane. I hope you can see the plot. What you now see is, I'm going to close that because I don't like the solution. understand much better. All right. So what you see now is a 3D plot. And so we have x1, x2, and x1 squared. These are the coordinates of the points you do see. And in this case, we don't have stars and circles. We have red filled dots and open blue dots. So we have a two-class problem. The same one that's plotted on the exercise sheet, but now in 3D. And as you can see from this plot, and I hope you can see, yeah? If not, please let me know. You can see that there is a separating hyperplane, a three-dimensional, that separates this expanded classification problem perfectly. The red dots lie on the left-hand side and the blue circles lie on the right-hand side. And you can move it around and around, and you will see this is a separating hyperplane, right? Okay, so if we move it there, the blue dots are on this side, and the red dots are on the other side. All right? Okay. Basically, there are some slides now as a solution to this exercise where I can see these kind of plots, right? Screenshots. Are there questions remaining? We can read, yeah?
Professor, to the task B, we using, the question is, we using a higher dimensional input for the separating, or if it's separating or not. We say yes, but I still don't understand how that works on the dimension space, how it looks when we use this X. When
X1 squared?
Yes, this is my problem. Yes.
Okay, this is basically the classification problem you get when you use x1 squared as an additional feature.
Okay.
The red and the blue dots.
Okay.
All right?
Yes, okay.
Okay.
Thank you.
Yeah? Okay, and you now see that given this expansion, right? You see you transform the initially the problem that is nonlinear separable in two-dimensional space now becomes linear separable. And we do see the separating hyperplane. We can learn it. Okay?
Yes.
All right. Other questions? Oops. We can redo this. Over and over again. I hope all right. Okay. So it's not always the same hyperplane that we have come up with. Okay. That's slightly skewed now. Depends on the initialization, which one, where we end up. Okay, so if there are no questions remaining regarding this problem set number 3, I would like to move on. Are there questions? Yeah, somebody has the mic on. I switch it off. Okay. All right. Okay, so we also worked on exercise sheet problem set number 4. This is about linear nets. Okay, problem set number 4. Last time we were able to go through the questions of task 1. I summarized the answer of these questions on an additional sheet that's available in the Moodle course. Have you seen that? Okay. So maybe we go through, I mean, oh God. So we have different question here. So the first line is the learning, the OYA learning rule. We spent some time to derive this learning rule. We also saw the extension of OYA's learning rule to a learning rule that can be applied to all neurons in a linear layer. That's Sanger's learning rule. It's a bit more complicated here in this term that does the regularization. So the first question was, is it supervised or unsupervised? The question is pretty easy. It's unsupervised because we are not using target values for input vectors X. So we know from derivation of this learning rule that we have to be quite careful about having a stable learning algorithm. So what we should do is we should start with weight vectors that are initialized according to the criterion that they satisfy the condition that their length is 1. It's easy to get this because you just have to normalize the weights of the individual weight vectors by the norm of the weight vector. The stopping criteria for this kind of unsupervised learning rule, it's a bit tricky because what you have to observe is how do weights change over time. When you got a stable solution, that means weights are marginally changing over time. You ended up with this is where you are going to stop learning. The problem is, what do we learn using this learning rule? We've analyzed that, and what we came up with is that we are learning the principal components of the data distribution. That means the direction of space in which the data cloud scatters most, second most, and so on. Okay, and the weight vectors given the problem, right? And what we are doing is we are basically diagonalizing the covariance matrix, and this gives us a set of orthogonal vectors, the so-called eigenvectors of the covariance matrix, and they are orthogonal to each other. So we have perpendicular directions, and we represent the data in a new coordinate system. And the good thing about that new coordinate system is that the covariance between individual features is 0. So we have decorrelated data points. Okay. And the last question is, how can we compute the eigenvalues? Because this implementation of principal component does not calculate eigenvectors and eigenvalues directly using a numerical algorithm. So the only thing we have are the eigenvectors. To come up with eigenvalues in this algorithm, you actually have to calculate the covariance matrix, and you have to then estimate the eigenvalues using the eigenvectors you've learned by Oya's learning. I'm trying to show you the solution sheet for that I put together. Oh. Okay, so these are the answers. Basically, no, it is an unsupervised learning rule, hence target values labels are not required or used. I mean, it's not a problem if they are available, but they are not used by this learning algorithm. Part B, make sure that the weight vectors you start with are normalized. Part C is, when do you decide that learning has terminated, or you are on the safe side to terminate learning? You've learned the representation is, you observe the change in the weight vectors from one iteration to the other, right? And as soon as this has dropped below a small number, epsilon, which is a hyperparameter of this algorithm, you may stop. Okay. This is part D. What we know is the weight vectors that we learn with this learning rule, they converge to the eigenvectors of the data covariance matrix. The important thing, usually, I mean, if you do not mean center data, this is the correlation matrix. The interpretation of the weights, in this case, if you don't mean center data, it's quite complicated, right? So it's not the usual application. So what you do with your data prior to applying a linear network is you mean center it. So the data scatters around the origin of your feature space, of the input space, right? So, and what you learn with the learning rule of Sanger is you learn the principal components, the direction of scatter of this data distribution, in which the data distribution scatters most. That's the weight vector 1. And weight vector 2 is perpendicular to that weight vector and gives you the direction with the next largest variance in space. And since we only can draw this for two-dimensional space, that's a visualization in two-dimensional space. So we have x1 and x2 inputs. That's the data distribution. And since we have two inputs, we can have two layers, two neurons in our linear net. And these are the weight vectors that are learned by the learning rule of Sanger, right? Okay, so these are the eigenvectors of the covariance matrix. And this is part C. Part E, how do we compute the eigenvalues? Because our learning algorithms only gives us the WIs, the weight vectors, right? we don't get lambda i's from the eigenvalues. If we are interested in the eigenvalues, we have to compute them using the covariance matrix. So on the left-hand side here, you see how you can get the eigenvalues. So this is the initial equation, right? So what we are solving is we are looking, or we solve the equation here that a vector that's multiplied with the covariance matrix equals the same weight vector multiplied by a scalar lambda. So when we look at this equation, we can multiply both sides of this equation from left-hand side with the weight vector transpose, right? Since lambda I is a scalar, it doesn't matter. So we have the weight vector transpose times the weight vector, and we know that this is 1, right? Because we have normalized weight vectors. Okay. So given this equation here, taking the weight vector transpose times the covariance matrix times the weight vector gives us the eigenvalue for this eigenvector Wi.
Professor?
Yeah.
I have a question. I think you explained us this question in the past, but in the vacation I tried to understand something, because by the linear networks, when we try to learn with the Hebbian learn rule, we note that this doesn't work, because my weight vector is growing and growing and growing, because you tell us with the decreasing and increasing, when 2 neurons are activated, or 1 new neuron, that will be decreased. And because of this, we try it with the Euler rule to stop the growing of the weights. This is right, yes? This is the main thing, yes?
Yeah, the Euler learning rule is a regularized Hebbian learning rule, because the Hebbian learning rule by itself, the naive one, is not
Yes.
stable.
Can you explain me, please, in small words, when it's okay for you, the diagram of number D? I still try to understand how it works, how the weights are learning. This I want to understand.
Oh, you have to look at the math.
Yes.
Honestly. Because we have derived the learning rule step by step. So we started with, we analyzed that the initial learning rule, the correlation of input and output,
Yes, yes,
right, is unstable.
Yes.
This is the system of differential first order differential equations, right? So this is the part. This is just showing you it's unstable. There's a proof of it. This is not so important. This is just an add-on, right?
And
but then it becomes more important. The other stuff is more important. So what we said, okay, we have to somehow ensure that the weights don't grow infinitely, right? Just the learning rule tends to just increase the length of the weight vector, right?
Yes.
Okay. So, but what we want to do is we want to change the direction of the weight vector. So we said, okay, we have to guarantee that the weight vector doesn't increase in length. We force the weight vector to change direction. This is done by normalization. We started with explicit normalization after each learning step. That's a bit uncool, right? That's nothing you want to have. Then we did an implicit normalization, but normalization always involves that you have to know all the weights, right? To do the normalization. And this is called a global learning rule. Global learning rules are a bit tricky because it depends on the order you are determining weights, what the outcome is. So usually you want to have a local learning rule that just depends on the individual weight. And that's what we deduced in the next steps.
This is our second solution, the global learning rule.
So we did a Taylor expansion around alpha 0 equals 0, around a small learning rate, right?
Yes.
And
because I find it's a little bit
so we linearize the learning rate around the learning rule around the interesting learning rates, small learning rates. Next step.
And
then we saw, oh wow, there are a couple of higher order terms, including the learning rate squared. And since we assume small learning rates, these terms are not going to buy as much, right? So we neglect them. And that's the point where we ended up with Oya's learning rule.
Okay. Yes.
All right.
Yes. Okay. And
that's how we came up with the learning rule. And then we did the next step. We said, well, now we have this stable correlation-based learning rule, the regularized one. So, but what do we learn? Yeah, because we don't have okay, and this was the content of the next part of chapter 4. Okay, to see that in principle this learning rule solves this problem here. All right. Okay, and this is eigenvector and eigenvalue math. That's not really interesting. It's just to show you that to calculate the eigenvalue, we need to calculate the covariance matrix. Or put it the other way around, the cool thing about Senger's learning rule and linear nets is that we don't have to calculate covariance matrix to do PCA. We can do this without.
Okay.
All right.
And Professor, you say in the examination we have to calculate covariance matrix. You say it in last year. Yes, is it no? Okay.
No, you don't have. We haven't done that.
Okay.
Okay. Okay. Are there further questions remaining? If not, I would like to move on to the last exercise on exercise sheet number 4. We've done the simulation and we looked at how this learning behaves, right, with the synthetic data. There is a second exercise or second task. And that's nothing you're supposed to program. That's something we want to look at right now. So we already managed to do exercise task number 2. We looked at this simulation. We got some synthetic data and we saw that the learning rules basically compute the directions in space where the data cloud scatters. So exercise number 3 is now kind of application of this principal component analysis. So the question is to come up with a consumer price index. So what we will look at are prices for different products which are in a basket of goods, right? Products, 5 different products, and their prices for 23 different states in the US, different cities in the US. The prices are for bread, burger, milk, oranges, and tomatoes. So the data distribution for these 23 cities are given here in this scatter plot. So this is basically kind of looking at the data in respect to the different dimensions. So on the diagonal, we do see a histogram how the bread price is distributed across, or for the bread price is distributed. So this is a histogram, how expensive bread is overall, right? This is how expensive burgers are overall, milk, oranges, and tomato. Right? On the off diagonal of this matrix, we do see the correlation of bread and burger prices, right? There is obviously a correlation there, right? And we do see the different correlations for all the different combinations. That's what we can visualize. We cannot visualize the distribution of the data because input space is 5 dimension. Okay. Maybe for the diagonal, what we do see is that the mean price for bread, burgers, oranges, and tomatoes is slightly different. Okay, you can see it here. And it's not, I mean, it's kind of normal distributed, but not at all. Okay. So what we are interested in is we want to compute a price index based on this data given. So this price index should contain the price of bread, the price of burger, the price of milk, the price of oranges, and the price of tomatoes in a specific manner, in a weighted manner. So we would give, we want to give weight to each of these product prices to come up with an index or a number that tells us how expensive or cheap a particular city is. This looks a bit like, yeah, linear net, like PCA. So this is something we can solve with a linear net because we will get the direction of the price distribution for these different products where we have the most scatter. So we have 5 inputs. Input signal is 5. Yeah, the dimension of input space. How many training samples do we have? We have 23 cities. We have the prices of 23 cities. So Q is 23, K is 5. How many output neurons do you need for the solution of this problem? We want to an index, one number. So basically, this index will be the output of the first neuron in our network. Since we have input dimension is 5, we can have at most 5, maximal 5 neurons in our linear layer. What's a reasonable pre-processing of the data? since we know that these principal components are calculated from mean-centered data, we should mean-center the data before we apply the learning rule, the linear learning rule. Mean centering means that we subtract the average of each of the product prices, right? So we just see, so because the mean price, this is doesn't contribute much to the overall price of the city. We're interested in where does prices scatter most, right? And where do we see the most scatter to the left or right? Okay, so we are probably working with mean-centered data. So we do the simulation right now, and then we move on to the questions here. So we will see ordering of the cities according to their price level. We will also use standardized data. What's standardized data? So we have mean-centered data, we have standardized data. What does it mean if we do, after mean centering, we do a standardization of data? Okay, we are going to answer this question using the simulation. Okay. Okay, this is again the Octave window, so we don't go into the code. We start question, do you see something? Please question.
No.
No. Okay, thank you. Now you should see Octave, right? Do you see a window showing the data?
No.
No. But you see the development tool Octave. Yes or no?
In the background, yes.
In the background and in the foreground?
Black screen.
Okay, let's see. This is going to change. Try something else. Okay. Do you see now the window?
Now we see it, yes.
Yeah. Okay, you see cities.
Yes.
Red price versus the burger price. The scatter plot we have seen already on the exercise sheet, just one of these many. This is the raw data, right? Of course, we cannot visualize 5-dimensional space. So this is just one correlation that we can see here. And that's the raw data. These are basically the same parameters that we already know from the synthetic data. So we have the number of learning steps we are doing before we see the error here in the bottom. We have chosen a learning rate that guarantees us a stable regime for the learning rule. And we have this epsilon, which gives us, which indicates us a reasonable level of stability of the learning rule. So since raw data is not quite useful here for answering the question, we straight away go to mean corrected or mean standard data. And what you see, what's going to happen is now the mean price of all these cities is for bread and burger is 0, and we do see a scatter around this mean price. So we see the cities that are more expensive and cheaper than the mean price. Okay. Now this is just a particular view on the data. This is not the whole data cloud. Okay. So in this case, we don't visualize learning process here. In this plot, we visualize learning progress just here as the mean error or the change of the weight vector over time. And so I'm going to start to calculate this consumer price index now. And I'm performing 100 learning steps. And I'm wondering why I don't see any. Oh, start. Okay. Okay, I'm starting. And in the bottom, you will now see how the weights, how we are changing the weights now in the linear network. We're training a network with 5 neurons. And we watch the average change. And as you can see, we do have a change already, so we will have to continue. Okay, I think we've fallen kind of below this change, below the epsilon. Let's continue further. Decrease learning rate. Okay, that's fine. Okay, so basically this is the point where we reached the first time, or the update was the first time below the threshold we gave here. So what we do next is we look at what we've calculated. I hope you will see the figure. Nope. All right. Okay, that's the figure. That are the results. What do we see? Oh. Okay. What do we see? We see 4 different plots. We see weight vectors here in the bottom. So we do see the eigenvalues. And we do see the amount, the size of the eigenvalues. This is the absolute number of the eigenvalues. Of course, these eigenvalues are calculated using the formula given on the previous, in the answers for exercise 1. So they are not calculated by linear network, they're calculated afterwards. It's just to demonstrate you how much variance is included. So this is the absolute number of eigenvalues. We can normalize these eigenvalues. We can say, okay, the first dimension of this PCA space contains 60% of the variance in the data. So the second component contains a bit more than 20, and the third component goes down to 10, and the fourth component and the fifth component, they contribute below 10% of the variance, right? So this is basically okay. This is basically the distribution of variance along the different principal components of this space. On the lower part, we do see all the weights we calculated for different neurons. And honestly, if you look at, you have to start here. That's the bread price, that's the tomato, that's the burger, the weighting for the burger price, that's the weighting for the milk price, that's the weighting for the orange price, and that's the weighting for the tomato price of the weight vector of the first neuron in our network trained with Oya's learning rule. And these are the weight vectors of the other neurons in the network, right? They are pointing in the direction with the next amount of variance, and so on and so on. But here, let's look at the weighting of the different prices of for the consumer price index. So what we see from this is that the weight for the oranges, we do have significant weight for oranges loading, and we do have significant weight for tomato and burger. So the consumer price index basically relies on orange price, tomato price, and burger price. That gives us the most spread across the data, right? That contains the most variance. Yeah, the combination of these. That's basically how you interpret these results. Okay. That contributes to the price level of a city. Let me go back to the original figure. So I'm going to stop because we have more information there. Okay, so in the scatter plot here, now, you do see the first principal component, the output of the first neuron in the layer, so our consumer price index. And what you can see is, if you look along this axis, you see that Honolulu, which is located on Hawaii, that's a very specific city, right? That has a price index that's quite different from the rest. So on the right-hand side, we do see a group of cities, or we do see cities which are either cheaper or more expensive than Honolulu. They do have almost the same price level. And we do have a group of cities here in the middle, right? If we now look at the clustering, if we include the second principal component, so we look at the clustering that we observe using the first and the second output of the network. What we do see is we see a clustering. We see two cities, which is Honolulu and New York. They seem to have a very special price. level because they are off. We see a cluster of cities like Boston, Philadelphia, and Cincinnati. They seem to have the same price level. We do see here a cluster of cities, which I would say this is, I mean, these are cities on the west coast of the United States. Los Angeles, Seattle, and San Diego. And I mean, this is San Francisco. This also basically belongs to that group. And we do see a bunch of cities here which are located somewhere in the middle of the United States. Okay? So this is how you can interpret this. But the consumer price index would be just the value of the first principal component Y1, the output of the first neuron, right? And we've seen the weighting of the individual input components to the network, how they contribute to this price, consumer price index. All right. So this is what I tried to explain or finish up today in the lab. Are there questions regarding this application? Okay. If not, I would like to finish both exercise sheets for now. I mean, we can think about standardized data. Maybe let's say this is the last comment. Standardized data means that we are basically normalizing the spread of the prices. So we make sure that the prices of the bread, burger, and so on do have the same variance. That's standardized data. For the application of calculating a consumer price index, right? That gives us a clear definition of the price level of different cities. This is probably not a good idea to do, because if you normalize it, then you are losing any absolute information about the price scatter. All right, so which type of data you're using basically depends on the application you have in mind. You're feeding into the network. Okay. This depends on the particular application. I really want to finish the linear networks at this point. Today in the afternoon, we continue with chapter 5 because we have still something left to do in this lecture, and we move on to nonlinear networks. See you in the afternoon. I'm happy to meet you again in the afternoon. Any urgent things that are remaining?
Professor Bauer-Wösing, I write you an email because I have a little bit questions. Do you see my email?
Yeah, I saw it. I have to find out. I think probably by the end of the week.
Yeah, thank you very much. Thank you.
All right.
Thank you.
Okay. Okay. See you later.
Bye.
Bye.